Hello students, Sean McMahon here, and hopefully you're watching this video after watching the video on periodic table organization. And in that first video, we talked about how Mendeleev took all of the elements that he was aware of, and instead of putting them all in a straight line, he looked at patterns where certain elements had similar characteristics. And he stacked those similar characteristics in what we would call groups or families. So each group or family is basically a column going up and down. So this group, group 1 or 1A, is your alkali metals. And in that video, we also talked about the alkaline earth metals, group 2A. We talked about the noble gases. Everybody wants to be noble. 8A. We talked about the halogens, group 7A. And again, groups, families, their columns up and down. We also talked how the periodic table was organized by periods. Periods are our rows, left and right. So this would be period, and I'll say N equals 1, 2, 3, 4, 5, 6, 7, and so on. The one thing that I didn't talk about is if you look at the periodic table, we see these numbers. So for example, number 1 for hydrogen, number 2 for helium, 3 for lithium, 4 for beryllium, 5. What we're seeing is these numbers are increasing, right, sequentially, and they're going in order, 1, 2, 3, 4, 5, 6, 7, consecutively. And those numbers represent what this video is about, the atomic number. The atomic number is the number of protons. And we're going to find out that the periodic table is organized by atomic number, stacked in periods, rows, and vertically stacked in columns, which we call families because they have similar characteristics. So let's get on to it. So how do we identify an atom? The atomic number is how we identify an atom, and the atomic number is the number of protons. So a helium nucleus, right? If I have 2 protons, I'm helium. That's just how it is. If I have 13 protons, right, I'm going to be aluminum, no matter what. That's how I identify an element. It's based on the number of protons. So right here, if I look at the symbol Na, which is natrium, right? Because again, in those other videos, we talked about how a lot of these symbols were derived before the English language was so popular from Latin, Greek, mythological planets. So sodium, natrium, is Na. But really, it's the atomic number, which is equal to the number of protons that makes an atom sodium. So all sodium atoms have the atomic number of 11. That means they have 11 protons. Now, we also talked about last time that these atoms, right, they're neutral. So if I have 11 positive charges, right, due to the protons, well, to make the overall atom have a 0 charge, I have to have 11 negatives. So for every neutral atom, the number of protons is equal to the number of electrons. Those charges, those opposite charges, cancel each other out. So if I have 11 protons, I have 11 electrons. If I have 10 protons, I'm going to have 10 electrons in a neutral element. Now, what identifies the element is the atomic number, which is the number of protons. So how do I figure that out? The periodic table, the best cheat sheet, right? If you look at sodium on your periodic table, group 1A, period 3, you see it has an 11. That means it has 11 protons, right? So to be a sodium atom, to be sodium, you have to have 11 protons in your nucleus. Now, we're not forgetting about that there's neutrons in there. We'll talk about that in a second. But for right now, the focus is the number of protons, the atomic number, is what dictates what the element is. So in this model right here, right? Well, we look on the periodic table, right? It's organized by atomic number, the number of protons. So hydrogen has 1 proton, helium has 2, and lithium has 3. And when you look at the periodic table, lithium, right, has a 3. That's its atomic number. That's the number of protons. So that's what they show in this little atomic model. The red dots are my protons, right? So I have 3 positive charges. Well, again, this atom of lithium has to be neutral, right? So what do I also see? I see 3 electrons around outside of the nucleus, right? So a 3 plus, a 3 negative equals 0. There's a 0 charge on the lithium atom because it has 3 protons and 3 electrons. The lithium atom has to have 3 protons. That's what makes it lithium. If it had 4 protons, well, that's beryllium, right? If it had 5, that's boron. If it has 6, guess what it is? It's carbon. Carbon's atomic number is 6. What do I mean by atomic number, right? That just means 6 protons. So it has 6 protons. Again, the red dots, 1, 2, 3, 4, 5, 6. So because it has 6 positives, what does it have to cancel out that 6 plus charge to be a neutral atom? That's easy. 6 negatives. Where do I get the 6 negatives? Electrons, 1, 2, 3, 4, 5, 6. Now, again, the neutrons are there, right? So there's 6 neutrons in here. The white circles represent the neutrons, but the neutrons, remember, their symbol is O because they're neutral. They don't affect the charge, right? So there are 6 neutrons there. So just to sum up everything, the atomic number, right, equals the number of protons. And that's what determines what the element is. So if I have 1 proton, I'm hydrogen. If I have 2, I'm no longer hydrogen, I'm helium. So the way this table's working, it's showing the element, it's showing the symbol, it's showing the atomic number, which is the same thing. So all of the atomic numbers are the same as the number of protons. So there's a different number though. And actually, let me get back to that. The number of protons, right, the number is going to equal the number of electrons. Why? Because the positives and negative, they have to equal each other, right? So 1, 1, 7, 7, because all these atoms are neutral. There's another number you have to think about, and that other number is the mass number. So the mass number, let me erase this because I got a little static here. The mass number is the number of protons, right, plus the number of neutrons. So hydrogen, if it has 1 for an atomic number, 1 for a mass number, you would write it like this, 1, 1. Sometimes they'll write it like this, 1, 1. What that means, it has 1 proton, and it, based on its mass, it only has 1 proton as well, right? But then I look at nitrogen, right? Looks a little bit different. So how does it look different? Well, let me clean this up here. So nitrogen, you might write this as a 14,7. So what does the smaller number represent? The atomic number. And what does that atomic number mean? The number of protons. So when my atomic number for nitrogen is 7, the smaller number on the periodic table, that means I have 7 protons. Well, what does the bigger number mean? The bigger number, which we're going to call the mass number, right? So the mass number is the number of protons plus the number of neutrons. So 14 is my mass number. That's the bigger number. What's 14 minus 7, which is the number of protons? 14 minus 7 is 7. So I have 7 neutrons. Let's do it with a different element. Let's do it with chlorine, right? So if I look at chlorine, now look at this particular atom of chlorine, right? What does it say? It basically says chlorine, whoops, 3517. So again, what's the smaller number? It's the number of protons, which we call the atomic number, and that's 17. This is how the periodic table is organized. This is what determines that this is chlorine. There's 17 protons. This number, 35, is the number of protons and neutrons. And why is that? Well, the mass, if you remember from earlier videos, the mass of the atom comes from the nucleus, the protons and neutrons, which is basically one atomic mass unit, 1 AMU for each. So if the mass number is 35, what does that mean? That means I have a total of 35 protons and 35 neutrons. So how many neutrons do I have? Well, if my mass is 35 and each proton and neutron is 1, if I subtract from 35 17 protons, what's 35 minus 17? 18. So what does that mean? I have 18 neutrons. And I mean, I could do the algebra for you guys. Here you go. Let me do the algebra, because some people might be getting confused. I'm talking a little fast. So 35 equals the number of protons and the number of neutrons. That's my mass number. 35 equals, well, the number of protons for chlorine is 17, right? That's the atomic number. That's what makes it a chlorine atom. 17 minus N, right? Or plus N, I'm sorry. If I solve for N, what do? It's just 35 minus 17, which equals what? 18. It equals 18. Now, some of you might be saying, well, Sean, what's going on right up in here? Why is there a mass number of 37 for this chlorine atom? That's a very good question. And nope, I make typos, I make errors. This is not a mistake. This has to do with the next topic, isotopes. Isotopes are where I can have atoms that have a different number of neutrons. And because the mass number is the number of neutrons and protons, if I have a different number of neutrons, I'm going to have a different number of mass. So how does this work? The smaller number is what makes an atom what it is. So this is my atomic number, right? And remember, that equals the number of protons. So all of these atoms of magnesium, the reason why they're magnesium, they have 12 protons. Otherwise, they wouldn't be magnesium. If they had 11, they'd be sodium. Remember that earlier on the video? If they had 13, they'd be aluminum. If you don't believe me, look at the periodic table. What's the number on the elemental symbol of aluminum? It's 13. It's in the 13 box on the periodic table. So because they all have an atomic number of 12 and they have 12 protons, they're all magnesium. So what's different about all of these? They're mass numbers. Well, this one's 24. This one's 25. This one's 26. How could that possibly be? How could they have different masses and all three of them are magnesium? Well, don't forget the mass number is the number of protons plus the number of neutrons. But it's the number of protons that identifies the element and makes it what it is. So because they all have 12 protons, they're all magnesium. They do have different masses. Why? They have different number of neutrons. And that, my friends, is what an isotope is. An isotope is an atom, right, of the same element with a different mass. So why do they have different masses? Oh, that's easy. If we're going to talk about the number of neutrons, what's 24 minus 12? 12 neutrons. What's 25 minus 12? This magnesium has 13. What's 26 minus 12? This magnesium has 14 neutrons, but they're all magnesium. Why? Because they have 12 protons. So isotopes. Protons are the only thing that determines what the atom is. So the periodic table is not only organized by periods and columns, or I'm sorry, rows, which are periods, and columns, which are called families or groups. It's not just organized by that, it's also organized by the atomic number, right? And that's the number of protons. So hydrogen has 1 proton. That's it. Otherwise, you're not hydrogen. So how is it possible that atoms of the same element have different masses? It's because they have different number of neutrons. That's what an isotope is. An isotope is an atom of the same element with a different mass. So that's the what, right? That's the what they are. The why, right? Why do they have different masses is because they have a different number of neutrons. So we got to figure this out, right? So the different types and amounts of each isotope is determined by nature, right? We don't have control of how often we see each of these different isotopes. We have no control of that. That's nature, right? But we have a way to show what nature gives us, and we use mass number and atomic number. So typically when we're writing elemental symbols, we want to show the mass number and the atomic number. And a lot of people always get confused. And they're like, oh, which one's which? It's easy. The smaller number is always the atomic number. Why is that? Because it's only the number of protons, and that's what identifies it as the element. So all of these are neon because they have what? 10 protons. The mass number is what can change in isotopes. So 20 is different from 21 and 22. Why is that? Well, that's because they have different number of neutrons. And it's not a neutron that identifies the element, it's the protons. So all of these have 10, so they're all neon. The reason why they have different masses is because both protons and neutrons have an AMU of 1. Right? So we can see if we're trying to figure out the number of neutrons for this isotope of neon, we'll call it neon 20. It has 10 neutrons. This one would have 11. Why? Because that's neon 21, or, isotope of neon 21. This would have 12 neutrons. All we're doing is subtracting. So here's a table showing a bunch of, well, not that many, but sorry, I get a little excited. It has some example of elements and the different isotopes are found in nature. Right? So here's one, right? Carbon 12, carbon 13, carbon 14, you might be familiar if you've taken any science courses. That's what we use for carbon dating. So it's an unstable nucleus, and over time, roughly about 5,780 years, it shoots out a beta particle and it ends up producing, nitrogen 14. That's another chapter. That's a whole other video. So I'm going to stay away from that. We'll get to it later. It's not that I'm ignoring it. I'm just going to wait. But if I look, carbon has 3 isotopes: carbon 12, carbon 13, carbon 14. However, all of these isotopes are carbon. Why? Because they all have 6 protons. What's the difference? The number of neutrons. Now, if you look at your periodic table, right? If you look on your periodic, go ahead and, if you have a periodic table, take it out. If you don't, you should always have a periodic table when you watch my videos. There's going to be 2 numbers in the box with carbon. You're going to see that, right? Some of you may even see more numbers, depending on the periodic table. You might even see this, okay? Don't worry about it. Let's just say you saw this. What people have to look at is the atomic mass, right? If I have 3 isotopes, 12, 13, and 14, the number that you see on the periodic table, the reason why it's not an integer, right? It's not exactly 12 or 13 or 14. It's a weighted average. It's based on how often we find each isotope in nature. And a lot of people, when they see this word average, they're they're limited. You know, because most people are like, well, wait a second, Sean, 12 plus 13 plus 14 divided by 3 is 13. That's not equal to 12.01. Yeah, that's right. Good for you. That's not a weighted average. That's what's called an arithmetic, right? Arithmetic mean or average. That's where you would find the frequency of 12, 13, and 14 the same. So the same amount of times. For every 12, there was a 13. For every 13, there's a 14. That's not how it happens with isotopes. Isotopes are found in nature with a different frequency. So we have to take into account that the average atomic mass is weighted based on how often we find these elements. Let's go back to the 3 isotopes of magnesium, right? You might look at this and be like, oh, wait, Sean, 24, 25, 26. God, I'm messy, I'm sorry. Divided by 3 would be 25. It's not. Look at the periodic table. What's magnesium? What does it show you? 12. What is it? I don't memorize this stuff. I just learn how to use it. 3.1 or 24.305. So what does that mean? These aren't found in equal frequencies. They're not found the same amount of times, right? In fact, you could look at this number and say, whoa, 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 it's closest to 24. So which one of these 3 isotopes do you think you find it the most often, the most frequently? Probably that isotope. Now, how did I figure that out? Well, isn't 24.31 closest to 24? And that's just how I look at it. So if my weighted average is closest to 24, right? It's 24.31 on the periodic table. That means this is the most abundant isotope. Am I right? Ooh, sorry, I'm messy. Am I right? Well, let's take a look. Where do I see percent abundance, right? Where do I see how often I find it in nature? Right there. Oh, look at that. What has the highest percentage in nature of the 3 isotopes? Yup, 24. It's found 78.7% of the time. Only 10.13 is magnesium 25, and only 11.17 magnesium 26. So it makes sense that because there's more magnesium 24, that weighted average is closer to 24. That's what I love about this little slide, right? If there's this many magnesium and I randomly pick one, chances are I'm going to pick one of these, right? Because it's in greater abundance. So that means that the weighted average is going to be closer to the most abundant isotope, which is isotope 24. And again, all of these are magnesium. Why? Because they have 12 protons. And it's the atomic number, the number of protons, which make these 3 isotopes magnesium. But right now, we're focusing on average atomic mass. So we have to take the mass number. Where do I get the mass number? That's that, the bigger number. Remember I said that? So the mass number is the number of protons and neutrons. So I have to take into account, these have different masses. So what would be the average weight of these 3 isotopes? But when I say average, it has to be a weighted average because it's based on how often I find one. So that's why you got those goofy decimals on the periodic table. Those aren't typos. They're taking account relative abundance, or another way of thinking it, the percentage of that isotope being found in nature, right? So it's a weighted average. So not all atoms of the same element have the same mass, but we can still calculate it, and we can still calculate the weighted average based on their relative abundance. It's easy. Well, how do we do that? We look at their percent, we basically multiply it by their atomic mass. So the atomic mass, right? We were talking about magnesium. It had 3 isotopes. This is what I want you to do. You take the percentage of one isotope, multiply by its mass. Then you're going to add to it the percentage of the other isotope, multiply it by its mass. Then you're going to add to it, if there's 3 isotopes, the percentage of that isotope and by mass. But remember, when you're doing the percents, right, because this is part over whole, you're going to turn that percent into a decimal, okay? It's got to be turned to a decimal. So I'll show you with this next example what I mean. By the way, the dot, 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 if there's more than 3 isotopes, you would repeat it. So if there was 4, what would I do? Percent isotope 4 times whatever the mass in AMU of isotope 4 is. And then I'd add all these up. So here we go. I got chlorine. It has 2 isotopes. Chlorine 35, so a lot of times they'll go chlorine 35. And its abundance, chlorine 35, is 75.77%. But remember what I said, you're going to change that to a decimal by dividing percents. There's part over whole or part over 100. Divide that by 100, you get 0.7577. Okay? Now, when they say chlorine 35, realize it's not exactly 35. It's 34.97 AMU. Why is that? Well, the protons and the neutrons, they're not exactly 1 AMU, so there's a little bit of a deviation, but they're pretty close. And then the other isotope of chlorine is chlorine 37, right? And we see that that abundance is 24.23. Now, if I wanted to change that, what am I going to do? Divide by 100, just move that decimal on over, right? Now, a lot of people will say, wait, they have different masses. Well, again, why are they both chlorine? They're both chlorine because they both have 17 protons, or atomic number 17. They have different masses because of the neutrons. But the whole point is, how are we going to calculate this, right? How are we going to calculate that weighted average, that weighted atomic mass? And a lot of you are smart. You're going to look at the periodic table and say, man, Sean, it's just 35.45. Yeah, but you're not showing me your work. I need to see your work, right? Anybody could look at a periodic table. So how are you going to show me your work? Well, just like the previous slide. I'm going to convert the percent abundances to decimals, like I said up in here. And then I'm going to multiply it by the individual isotopic mass. Now, if they give me the exact AMU, like they did right here, and they said that was 37, I'm actually going to use the AMU they give me. I'm not going to round it. I want to get as, accurate as possible. So don't round up, use those numbers. So how do we do that? Okay, well, here's the percent of isotope 1, and it's AMU of isotope 1, right? So I'm multiplying those, and I get that as a product. Then I take the isotope, so this is isotope 1. This is isotope 2. Right? So I take the abundance of that isotope, and they switched it on me on the slide, but you get it. This would be isotope 2. This would be isotope 1. I don't know why. But anyways, going back to here, I take the relative abundance of chlorine 35 right here, divide that puppy by 100 to turn it to a decimal. I get that. Then I multiply it by its AMU. I want to get that. And now I get this product. So what do? I add both products up. And what do I get? 35.45 AMU. That's what's on the periodic table, and that's why you see that, right? So this is the elemental symbol. Why? Because I take the first letter, I capitalize it, but it's not just C because carbon took that. So I have to go to a lowercase for the next letter in the symbol. I don't know why they didn't do H. They went to L, the third letter. Don't blame me. They just did that. I wasn't born. But so now I got Cl, that's for chlorine. This number is my atomic number right? Which is how I know it's chlorine, because that's what identifies it as chlorine, and that's the number of protons, right? So if I have 17 protons, doesn't matter, I'm chlorine. And this number on the periodic table is the weighted average atomic mass for all the isotopes. And in this case, there's two isotopes, the 35 and the 37, and we use their relative abundance and multiplied by, so we use their percentages, multiplied by their AMUs, summed it up, and we get the average. All right, that was a windfall. I apologize, but I hope you enjoyed the video. I hope it makes sense. Thanks for being patient. And if you have any questions, comments, just let me know. I'll do my best to answer them. Thanks for watching.